everyone, my name is Aisha Salanya, and today I'm going to be overviewing heat capacity, its importance, and how we can use its fundamental equation to determine different properties that different substances may have, and also to analyze different Excel models. So, heat capacity itself is defined as how much heat energy it takes, usually in joules, to raise a particular substance by exactly 1 degree Celsius or 1 Kelvin. And there's two main types. There's specific heat capacity and molar heat capacity. Specific heat capacity is the amount of heat energy it takes to raise exactly 1 gram of that substance by 1 Celsius or 1 Kelvin. And molar heat capacity is the amount of heat energy it takes to raise exactly 1 mole of that substance by 1 degree Celsius or 1 Kelvin. With that said, let's break down the heat capacity equation, which is defined as Q is equal to M times C times delta T. Q represents the amount of heat energy, usually in joules, that is absorbed or released by the substance, depending on its reaction, whether it's endothermic or exothermic. But basically, this equation is explaining how that amount of heat energy in joules will always be equal to the amount of mass that you are actually heating up or cooling down in your procedure in grams times the specific heat of that substance you are utilizing, multiplied once more by the actual temperature change that occurred after you completed your procedure. And the temperature change, you would just be subtracting your initial temperature from your final temperature. This equation, you're always going to be able to determine how much energy is truly needed to change the temperature of a certain amount of mass by only the temperature change of your experiment, the amount of mass that you're cooling or heating up, and the specific heat of that substance. The energy affects us today is through food, like blueberries. Using these heat energy calculations, we can actually determine how much energy is released after burning one blueberry. Thus, we can actually fully understand the calorie content in one and how much energy we need to use when wanting to burn off some of those calories that we've ingested. Understanding these fundamentals can allow us to compare and interpret different models shown in Excel, which I will be doing here with water and. Okay, so here you can see an Excel I made comparing water and octane. And you can see I decided to pick a sample or compare a 100-gram sample of each. However, since the specific or the molar specific heat that I used included moles, I decided to convert the mass sample into the amount of moles in that sample. Okay, so here you can see where I calculated Q in joules, the energy needed to reach that specified temperature, which I did using that same formula, multiplying the mass, the specific heat, and the change in temperature. And right here I'm just showing where I got all my variables to plug in. Okay, so after analyzing this graph, you can see that even though water has more moles in the sample than octane does, octane still seems to require more energy to reach the same temperatures as water. Thus, we can assume that octane most likely is a more complex molecule that can absorb more energy through its intermolecular interactions.